So we discussed last week about the calculation of density of the crystal, and that a very important formula that you have learned. So I tried to solve all different types of question, which is actually the type of question which are coming or which are asked in ISC exams. But one of your friend Rajdeep had put forward his doubt. This type of question I did not discuss. This is about when what is to be done, like how to calculate the number of atoms when you are given the mass of the element. Okay, now his question was as you can see there in a screen, an element has a body centered cubic structure with a cell age of 288 picometer. The density of the element is 7.2 gram per centimeter cube. How many atoms are present in 208 gram of the element? Now first we need to find out what is the volume. So volume is what is a cube. A cube means age length cube. So age length, as you can see there in his question only, already the first part was what was already solved. You can see here the first part was here this one, volume of the unit cell is already solved. So 288 picometer cube. So that picometer is what is being converted into centimeter cube. You can see 288 into 10 to the power minus 12. In fact, this is what is being converted into meter cube. Here it is meter cube, and after that meter cube is what is being converted into centimeter cube. In fact, here it is, you can see centimeter cube. So 288 into 10 to the power minus 10 centimeter cube. So you know that 1 picometer is equivalent to 10 to the power minus 10 centimeters. So that's why cube. So 3 of them are there, that's why cubed. So it is cubed. So that is volume of that particular cell is 2.39 into 10 to the power minus 23 centimeter cube. This is already solved. I think in his screenshot this first solved part has already come. Now let us see some extra things which are required. Now for that, what we will be finding is, since you are given total 208 gram, now you know we are here talking about only one unit cell. This is of only one unit cell, but then total mass is what is given to you. So there mass is what is given to you as 208 there in the question, 208, and density is what is given as 7.2. if you look at that question, 7.2 gram per centimeter cube. Then if I want to find volume, so which you have already learned in lower class, volume is what is equal to mass by density, and then this is what is 208 divided by density is what is 7.2. So this is what will come as 28.89. So since this is volume, so I'll take this as 28.89 centimeter cube. So that is what is the volume of 208 gram of that particular element. Now since the previous one, that one this is what is about this volume is what is about one unit cell, then let's see what is the total number of unit cell. How many unit cells we have? So number of unit cell is equal to total volume. So what is the total volume which we took out just now, divide by what is the volume of one unit cell. So total volume is 28.89 centimeter cube, and the volume which is already calculated there, as you can see on the top, is 2.39 into 10 to the power minus 23. So minus 23. So as you use your calculator to solve this, let me see, if you are using this calculator, then the calculator will give you, it will give you 12.09 into 10 to the power 23 is what is coming as the total number of unit cells. This many unit cells are there. Then you know that since the question is telling you BCC structure, so for BCC you know that the number of atoms present in one unit cell. So in one unit cell, that is what we call as your rank Z. The Z value is what is equal to 2 for a BCC. Then what is the total number of atoms present? So if you want to find the total number of atoms present in that 208 gram is equal to, so again don't forget, this is what is the total number of atoms present in one unit cell, and then the total number of unit cell, as you can see the total number of unit cell, this is present in one unit cell, and this is what is the total number of atoms. So since this is the total number of unit cell, and 2 in 1 and total number of unit cell is this. So if you want to calculate, then the total number will be equal to 12.09 into 10 to the power 23. This is the total number of unit cell, and in one unit cell 2 atoms are there, so there, multiply this with 2. So that is what is going to give you 24.18 into 10 to the power 23 number of atoms are present. And usually you know that decimal, so following the rule of power of 10, so that decimal, if you are placing at 2.4 rather than 24 point, so it is 2.418 into 10 to the power 20.
Magnetization of material. Matter is made up of atoms, which are made up of electrons and a nucleus. The electrons revolve around the nucleus in a circular orbit, just as current carrying loop constitutes magnetic dipole moment. Electrons moving in these orbits also constitute magnetic dipole moment. Beside the orbital's motion, the electrons also have a spin motion along an axis similar to Earth's rotation. This spin also constitutes a magnetic moment which has a fixed magnitude of 9.285 into 10 to the power minus 24 joule per Tesla. The nucleus has a magnetic moment, but it is very negligible when compared to that of electrons. The resultant magnetic moment of an atom is the vector sum of all the magnetic moments in an atom. The resultant magnetic moment of an atom depends on the number of unpaired electrons in the atom. Some atom contains paired electrons in all their orbitals. For the sake of understanding, let us consider helium atom, which contains only one pair of electrons. The paired electrons have orbital motion and spin opposite to each other. Due to this, the magnetic moment of paired electrons have some magnitude but have opposite direction. The magnetic moments would then cancel each other out, and the resultant magnetic moment will be zero. Some elements have unpaired electrons in their orbitals. In such atoms, the magnetic moment of the unpaired electron is not cancelled due to the absence of the paired electron. Due to this, the resultant magnetic moment in the atom will not be equal to zero. The atom behaves like a tiny bar magnet. Every material consists more than one atom. Generally, the magnetic moments of these atoms are randomly oriented, and the net dipole moment of the material is zero. However, when the material is placed in external magnetic field, the magnetic moments of these atoms tend to align themselves to the magnetic field and develop a net magnetic moment. Now let's discuss about an important term called magnetization, also called as intensity of magnetization. When a magnetic material is subject to magnetizing force, the material becomes magnetized and develops a net magnetic moment that is not equal to zero. The intensity of magnetization helps us to measure to what extent the material is magnetized. It is defined as magnetic moment developed per unit volume of the material placed in the magnetizing field. Magnetization is equal to magnetic moment by volume. Magnetization is a vector quantity and its SI unit is ampere per meter. Before continuing the topic, let us learn about few terms. Magnetic flux density. Magnetic flux density is the measure of the number of magnetic field lines passing through the unit area normally. It is also known as magnetic field. It is a vector quantity and it is denoted by symbol vector B. Diamagnetism. In diamagnetic materials, the atoms contain fully filled paired electron orbitals. The vector sum of magnetic dipoles of all orbital electrons is zero. Hence, no permanent magnetism is found in such substances. At atomic level, the electrons revolve around the nucleus due to the centripetal force acting on it that is directed towards the center. Also, The velocity of the electron depends on the magnitude of centripetal force acting on it. When the diamagnetic material is placed in an external magnetic field, each of the orbital electrons experience a mechanical force called Lorentz force. The direction of the Lorentz force depends upon whether the electron is moving in clockwise direction or anti-clockwise direction. If the electron is moving in anti-clockwise direction, the Lorentz force acting on the electron will be in radially outward direction. Since these two forces are acting on the same line and in opposite direction, the effective centripetal force acting on the electron will decrease. Due to this, the velocity of the electron will also decrease. Hence, due to decrease in velocity, the magnetic dipole moment of the electron will decrease. On the other hand, in the case of electron which is moving in clockwise direction, the Lorentz force acting on the electron will be radially inward direction. Since these two forces are acting on the same line and in same direction, the effective centripetal force acting on the electron will increase. Due to this, the velocity of the electron will also increase. Due to increase in velocity, the magnetic dipole moment of the electron will increase. Similarly, all the electrons in various orbits experienced a change in magnetic moment. Some become short and some become long. Due to this, the atom develops a net magnetic moment in the direction opposite to that of the applied field. Paramagnetic materials. The atoms of paramagnetic materials have unpaired electrons in their orbits, due to which they have a permanent dipole moment. In the absence of external magnetic field, the magnetic moments of atoms are randomly oriented and the net dipole moment of such material is zero. When an external magnetic field is applied, the magnetic dipoles experiences a torque and tries to align in the direction of the applied magnetic field. At the same time, the thermal energy of the material opposes the alignment and tries to keep the dipoles in random orientation. Due to the opposing factors, only small number of dipoles align in the direction of magnetic field, and the magnetization intensity of that material will become non-zero. The magnetization of paramagnetic material depends on two major factors: temperature and external magnetic field. As the magnetic field increases, more number of dipoles can overcome the thermal energy and align with the magnetic field. The magnetization of the material increases. When temperature of the material is decreased, the thermal energy of the material decreases. Now, more number of dipoles can overcome this lower thermal energy and align with magnetic field. The magnetization increases. Again, if the temperature is increased, the thermal energy of the material increases. Now, some of the dipoles that already were aligned experience higher thermal energy and become randomly oriented. The magnetization decreases. Now, instead of external magnetic field B, it would be appropriate to use the term magnetic intensity H, which is the actual source of magnetic field. It is given by H is equal to B by mu. Therefore, we can say that the intensity of magnetization of paramagnetic materials is directly proportional to the applied magnetic intensity and inversely proportional to the absolute temperature. M is proportional to H by T. Removing the proportionality sign, the equation can be written as M is equal to C into H by T. Here, the constant of proportionality C is called Curie constant. Now let us discuss about an important term in magnetism called magnetic susceptibility. The magnetic susceptibility of material indicates how much a substance becomes magnetized when it is placed in an external magnetic field. It is denoted by this symbol, chi m. Magnetic susceptibility of material is defined as the ratio of intensity of magnetization m to the applied magnetizing force h. Chi m is equal to m by h. Since h and m have same units, the magnetic susceptibility is a unitless quantity. Now, if we consider this relation, m is proportional to h by t. This relation can be rewritten as m by h is proportional to 1 by t. Now let us replace m by h by magnetic susceptibility. Now, from this relation, we can say that magnetic susceptibility of a paramagnetic material is inversely proportional to absolute temperature. This relation is called Curie law in magnetism. The Curie law has certain limitation. Let us discuss about it. Earlier we have learned that the magnetization of paramagnetic material increases with increase in applied field. The magnetization also increases when the temperature of the paramagnetic material decreases. In both of these cases, after a particular point, the magnetization does not increase even after increase in field or decrease in temperature. This is called saturation of magnetization. At saturation, almost all the dipoles in the material are aligned with the magnetic field. It is to be noted that Curie's law is applicable only when the magnetization of the material is far away from its saturation. Properties of paramagnetic materials. 1. A paramagnetic material is very weakly attracted by a strong magnetic field. 2. When a paramagnetic substance is placed in external magnetic field, some of the dipoles inside the material align in the direction of magnetic field. The material is weakly magnetized and acts as very weak bar magnet with north and south pole. Now, the magnetic field lines produced by this material are in the direction of external magnetic field inside the material, and the field lines are opposite to external magnetic field outside the material. The resultant magnetic field will look something like this. The magnetic field here looks as if they prefer to pass through the paramagnetic material rather than air. The magnetic field B inside the conductor is more than the external magnetic field B. 3. Since the magnetic field B inside the material is greater than the external magnetic field B naught, the relative permeability mu r is equal to B by B naught is always greater than 1. The magnetic susceptibility chi m of paramagnetic material varies inversely with absolute temperature. That is, chi m is proportional to 1 by T. The magnetic susceptibility of paramagnetic materials has a small positive value. 4. When a paramagnetic material in the shape of a rod is suspended freely in strong uniform magnetic field, the rod experiences a force and comes to rest in such a way that its longest axis is along the direction of the magnetic field. Ferromagnetism. In ferromagnetic materials, the atoms contain more number of unpaired electrons. For example, iron contains 4 unpaired electrons. Due to this, the net dipole moment of an individual atom is more compared to atoms in paramagnets. The dipole moment of one electron strongly interact with the dipole moment of the neighboring atoms and align themselves in a common direction. This small group of atoms with dipole moments in same direction is called a domain. A ferromagnetic material as a whole is made up of very large number of such domains. In the absence of external magnetic field, the dipole moment of different domains are oriented randomly in different directions. The dipole moment of one domain cancels the dipole moment of other domains, so that the net magnetic moment of the entire material is zero. In the presence of external magnetic field, the domain starts to align in the direction of applied field. The magnetization intensity becomes non-zero. Currently, since the external magnetic field is weak, only one domain has aligned with the external magnetic field. As field gets stronger and stronger, more and more number of domains start aligning with the external magnetic field. The magnetization intensity goes on increasing. Then, for a particular strong magnetic field, the magnetic moments of all the domains get aligned in the direction of magnetic field. Now, the material is at its ultimate stage of magnetization. Now, magnetization does not increase even if the external magnetic field is increased. This stage is also called saturation of magnetization. Just like paramagnetic materials, ferromagnetic materials are also influenced by temperature. When a ferromagnetic material is heated due to thermal energy, the dipole moments within the domain start coming out of the alignment and become random. The randomization goes on increasing. Then, at a particular temperature, the domain structure becomes completely destroyed and the ferromagnetic substance becomes paramagnetic substance. This particular point is called Curie point. Curie point or Curie temperature is defined as the temperature at which a ferromagnetic material becomes paramagnetic material. The Curie temperature of iron is 1043 Kelvin and for cobalt is 1394 Kelvin.
Conductors. The solids which have conductivities range from 10 raised to 4 to 10 raised to 7 per ohm meter are known as conductors. Metals have conductivity in the order of 10 raised to 7 per ohm meter and hence are the best conductors of electricity. Conduction of electricity in metals. Metals like gold, copper, aluminium, etc. are very good conductor of electricity. They can conduct electricity both in solid and molten form. The extent of conductivity in solids depend upon number of valence electrons. In metals, the valence band is partially filled and usually overlaps with the empty conduction band in such a way that there is no forbidden gap present. As a result, the electrons from the valence band can easily move to the conduction band. This results in conductivity in metals. Insulators. Those solids which do not allow electricity to flow through them are known as insulators. Conduction of electricity in non-metals. Non-metals like plastic, rubber do not conduct electricity. In these solids, the valence band is full while the conduction band is empty. Even the forbidden energy gap between the valence and conduction band is large. As a result, huge amount of energy is required to excite the electrons to the conduction band. Practically, it is impossible to provide this huge amount of energy to excite electrons and conduct electricity. Therefore, most of the nonmetals are insulators. Semiconductors. The solids which have conductivities between conductors and insulators ranging from 10 raised to -6 to 10 raised to 4 per ohm meter are called semiconductors. Conduction of electricity in semiconductors. Their conductivity of semiconductors like silicon, germanium, etc. are based on temperature and addition of impurity. In semiconductors, the valence band is almost full, while the conduction band is mostly empty. The forbidden energy gap is quite narrow. Thus, the heat energy available at room temperature is sufficient to excite some of the electrons from the valence band to conduction band, which results in the conduction of electricity to some extent. The conductivity of semiconductors increases with increase in temperature, since more electrons can jump to the conduction band. Now, let us study types of semiconductors and how conduction of electricity takes place in semiconductors. Types of semiconductors. These are two types of semiconductors. Intrinsic semiconductors. The semiconductors which can conduct electricity in their pure form are called as intrinsic semiconductors. At room temperature, the conductivity of these semiconductors are quite low. Example: germanium and silicon are intrinsic semiconductors. The process of adding small amount of impurity to an intrinsic semiconductor is known as doping, and the impurities are called dopants. Extrinsic semiconductors. The semiconductors which are formed by adding impurity to an intrinsic semiconductor are known as extrinsic semiconductors. Example: when germanium is doped with arsenic as impurity, it becomes extrinsic semiconductor. Now, we know what is doping. Let us study how an intrinsic semiconductor can be doped. Doping can be done in two ways: with electron-rich impurity or with electron deficiency impurity, as compared to the intrinsic semiconductor. Electron-rich impurities. Both silicon and germanium belong to the group 14 of the periodic table and have 4 valence electrons each. When silicon is doped with small amount of group 15 elements such as phosphorus, arsenic, its electrical conductivity increases. In pure silicon, each silicon atom uses its 4 valence electrons for the formation of 4 covalent bonds with the neighboring silicon atoms. When silicon is doped with some group 15 elements, then some of the positions in the lattice are substituted by atoms of group 15 element. The group 15 elements have 5 valence electrons. After forming the 4 covalent bonds with silicon, one excess electron is left on them. Since this electron is not involved in bonding, it becomes delocalized and contributes to the electrical conduction. Silicon doped with the group 15 elements is called an N-type semiconductor. The increase in conductivity is due to negatively charged electrons. Therefore, semiconductor doped with electron-rich impurity is called N-type semiconductor. Electron-deficient impurities. Electrical conductivity of silicon or germanium can also be increased by doping with group 13 element such as boron, aluminium or gallium. Group 13 elements have only 3 valence electrons. When silicon is doped with some group 13 elements, then some of the positions in the lattice are substituted by atoms of the group 13 element. The group 13 elements have only 3 valence electrons. Thus, they form only 3 covalent bonds with silicon. One of the valence electron of the silicon remains unpaired. This causes an electron vacancy or electron hole in the system. To fill this vacancy, an electron from the neighboring atom jumps into an electron hole, creating an electron hole at its original position. When the electric field is applied, electrons migrate towards the positive electrode by filling the holes, making it appear as if electron holes are migrating towards negative electrode. These holes are responsible for electrical conduction, and the resultant semiconductors are known as p-type semiconductors. Effect of temperature on electrical conductivity. Electrical conductivity of metals decreases with the increase of temperature, whereas the conductivity of semiconductors increases with increase in temperature. Why? In metallic crystal, the electrons are free to move throughout the crystal. However, the metal ions are fixed in position and can only vibrate. When a metal is heated, the metal ions start vibrating more vigorously, and as a result, motion of the valence electrons through the crystal is hindered. Thus, electrical conductivity of metals decreases with increase in temperature. In semiconductors, the energy gap is very small. A slight increase in temperature or on the application of small voltage, some of the electrons from the valence band jumps to the conduction band and show low conductivity. Substances exhibiting this type of behavior are known as intrinsic semiconductors. Examples: silicon, germanium, etc.
Now let's start with the structure of the four crystals which are there in a syllabus. The first one is sodium chloride, second we'll discuss copper, third one is the structure of diamond, and the fourth one is the structure of graphite. A very brief description about the structure is what I'm going to start with. In fact, you need only this. In fact, I'll give you in point wise, if possible, this in the form of notes, in the form of pointers. It will be easy for you to study, so I may put it there in the download description. Alright, now let's start then with the structure of NaCl. Now, as you can see there in the picture, so I'm taking the help of the picture, it will be a lot more easier for me to explain to you that one. Now, if you see those blue dots and red dots, now they actually represent the two different ions. Sodium ion, as you can see, are represented by the red dot, and blue color is what is actually the representation of your chloride ion. Now, if you can see, chloride and sodium, how are they arranged? Now, chloride ions are located at the 8 corner. As you can see, 8 corners. Look at the 8 corners. All blue color is what you will be seeing here. 8 corner, starting with 1, 2, 3, then 4, then again you have here 5, 6, and 7, and 8 corner there. So chlorine or chloride ion is located at the 8 corner, but it is not only at the 8 corners, and it is also located at the 6 faces. So 6 faces. Now look at where those 6 faces are. Here it is on the top. Here one face like this. You know, since it is a cube, so there are altogether 6 faces. So in the 6 faces there will be 6. So that means if you really count the number of blue dots that you see there, so it is 8 at the 8 corners, and 6 faces 6. So 8 plus 6 is what is making it 14. Now we are going to calculate actually what is the total number of chloride ion a little later, but then as such, now you just see where they are. They are located at the corner, 8 corners, and they are also located at the faces. I am talking this about chloride ion. Now going to sodium ion, where do you see sodium ion? Sodium ions are located at the 12 edge centers. Okay, now let me change the color a little bit. Okay, so I think I'll use a green color. Okay, now see where they are located at the 12 edge center. Now what is the meaning of edge center? Now look at the red dots. Edge, if you are looking about this edge, then look at the middle. So in the center of that edge is that one here, sodium ion. Here is another one, third, fourth. So this is the four, these are the four edges on the top. And same kind, if you count the total number of blue dots in all the other faces also, the total number of blue dots which will come will be 12. And in addition to that, so since it is a body centered, so that's why you will also be finding one somewhere in the middle. Body centered means one will be somewhere there in the middle. Body center is in the center. So that is what will be in fact the total number of your sodium ion. Now then let us see. Now I'll just list it out. Now what we discussed just now. So the total number of chloride ions and also the total number of sodium ions and where they are located. Okay, very very important. Number one, I should tell you, is point number one, that this is a phase centered cubic arrangement, or we can call it as chloride ion is FCC arrangement. Chloride ion. So this is FCC arrangement. So as you can see, they are located at the faces. Whereas the sodium ion, where are they located? Sodium ion, they are occupying the octahedral. They are occupying the octahedral voids. So wherever those octahedral voids are, that sodium ion, that red dots that you see, sodium ion are located at the octahedral voids. Then second thing that we have to discuss is, number two is, that what is the total number of chloride ion. As I already discussed, chloride ion, where they are at the 8 corners. Then if I really want to calculate what is the total number of chloride ion and sodium ion, then here it is. For chloride calculation, 8 corners. As we know, 8 corners into 1 corner is equivalent to 1 by 8. So that is what is equal to 1 chloride ion. Then we also discussed that chloride ion are also at the faces. Faces means there are 6 faces and one face is what is equal to half. So that is what is equal to 3. So the total number of ions, chloride ion present in one unit cell of sodium chloride is 4. This is the calculation of chloride ion. Now same way, if I want to calculate sodium, the total number of sodium ion, then as we discuss about 12 edge centers. So 12 edge center, and one edge of a unit cell is being shared by 4 unit cell. So that's why it becomes 1 by 4. So that is what is equal to 3. Then sodium also has one body centered somewhere in the middle. So here also the total number of sodium ion present in one unit cell is what is 4. So that means we have altogether 4 chloride ion and 4 sodium ion. Then what is the ratio? Now next thing is, what is the ratio between R plus, okay, I'll write this as R plus, which is sodium, and R minus, the radius of that chloride ion. That ratio in sodium chloride is what is 0.525. The ratio between this ion, sodium, to chloride, cation to anion, is 0.525. Now if you look at the diagram again, one sodium ion is surrounded by 6 chloride ion. Now that means if you are looking at the red dot, one red dot is altogether surrounded by 6 blue dots. Similarly, one blue dot is surrounded by 6 red dots. That means sodium ion is also surrounded by 6 chloride ion, and one chloride ion is also surrounded by 6 sodium ion. That is why we say the coordination number. So since there are two, usually coordination number is what is the total number of particles surrounding one particular this one, or it is in contact with that one particular particle. But since here we are talking about sodium also and chloride also, therefore if you are asked what is the coordination number of sodium chloride, then the coordination number of sodium chloride is 6:6. So this is actually how we calculate your total number of ions. So that is why if you really want to find out what is the formula of sodium chloride, I am going on to the formula. Since sodium, total number of ions of sodium is 4, so Na4, and total number of chloride ion is also 4. So 4 plus 4 is what is, in fact, common factor is what is 4. 4 ones are 4, 4 ones are 4. That is why the formula of your sodium chloride becomes NaCl. So this is what is the formula of sodium chloride. Let's now see the structure of copper. Now, unlike sodium chloride, copper unit cell is made of similar kinds of atoms of copper, all of them. Not unlike in sodium chloride, there were two kind of ions, sodium ion and chloride ion, but in copper only one kind of atom present, and that is what is copper. Everywhere those dots that you see, all the dots that you see, the balls that you see there, they are actually nothing but they are all copper atoms. These are all copper atoms. Now to discuss about what exactly you should know about copper crystals. Okay, first, now here let me write, like in case of sodium chloride what I did, let me do the same thing for copper. So the first thing is that copper is FCC arrangement. Okay, that is very important that you have to know. So copper atoms are arranged in FCC, so face centered cubic arrangement is number one. Then where do you find this copper? Now you don't have like a sodium or a chloride ion, like you don't have it two different kind of ions. Here you have only one atom, and that is what is copper atom. Now each of the copper atom or copper ion, where or what do they occupy? So copper ion occupy the 8 corners, and they also occupy the faces of the unit cell. So they will be occupying the 8 corners as well as also the faces of the unit cell. Now this will help us actually to calculate what is the total number of atoms present. Then third one, now let's calculate the coordination number. Now you know that one particular atom of copper or ions of copper is on the same layer is surrounded by 6 other different copper ion, and just above it in the upper layer it is again touched by 3 different copper ion, and on the lower layer, that is third layer, also 3 copper ions will be surrounding. That means now if you are talking about one particular, okay, let's talk about one particular here in this case, if you are talking about one particular copper atom, then on the same layer, in the same layer 6 of them, upper layer 3 of them, lower layer 3 of them. So that means the total number of ions of copper which is touching one particular ion of copper is 12. So that means we will say coordination number is 12. Again I am repeating, 6 on the same layer, 3 above, 3 below. So the total number of ions of copper which is touching one particular ion of copper is 12. So therefore we say coordination number is 12. Then now, like in taking into account what we have discussed in number 2, point number 2, now let's count what is the total number of particle present in, or total number of copper ion present. So total particle, so particle present can be easily calculated. We said about 8 corners, so corner means you know is 1 by 8, so that is what is equal to 1. And we also discuss about faces. Since we discuss about faces, 6 faces, so 6 into 1 face is what is equivalent to half, and that is what is equal to 3. So that means the total number of particle present in copper also is 4. This is what is the structure of copper. So sodium chloride we have seen. Now this is what is the structure of copper. Now going on to the next structure, which is let's go for a diamond. Okay, now this is what is the structure of diamond. Now it may look very complex here, but then again I should tell you that okay, here now when you really want to make a structure, you can make only this much. So here this is what we usually make as the structure of diamond. So you can see total number of carbon atom 1 2 3 4. So this is again 1 2 3 4 5. Usually when you make the structure, we make it this way with this only 5 only, but then so many different atoms of carbon are attached from one point to the other point, from one which is giving rise to a very very long chain. Now then let's discuss about this point of for structure of carbon. By the way, I am not discussing in detail, I am discussing very very little only what is required for you for your preparation for your ISC exam. So that only is what I am going to discuss. Okay, now the first thing that you have to know is that carbon atoms, they are sp3 hybridized. Now you already know what is hybridization. So in class 11 you have learned about what is hybridization, what kind of hybridization. Now then, as it is sp3 hybridized, each of the carbon atom, each means one, each carbon atom is tetrahedrally bonded, tetrahedral. So tetrahedral, or it is tetrahedrally bonded. Okay, this is what you have to know as the first point. So sp3 hybridized, and each carbon atom is what is tetrahedrally bonded. And so number 2, again we will discuss about coordination. So coordination number is 4. So that means one carbon atom is now surrounded or in contact with another 4 carbon atom on all around it. So that is coordination number 4. And the third thing is carbon to carbon. So this bond length, so from carbon to carbon, so from carbon to another carbon atom, this bond length, okay, here bond length is 154 picometer, and the bond angle, now again I'll point out what is the meaning of bond angle. So okay, let me use this color. So bond angle means here between this to this, here this bond angle. So this very bond angle is, okay, like if I write, so the bond angle is a normal bond angle for a tetrahedral structure. You know, this is what is normal, 109 degree and 28 minute. Usually we may call it as in approximately we can call it as 109.5 degree is what we may call this one as. So this is what is a normal. So this is not a distorted geometry, this is a regular geometry of tetrahedral. This is what is the structure of diamond. Now going on to the next one and the last one, I think we discussed with NaCl, then after that we discuss copper, then graphite, and the last one that we need to discuss is graphite. Okay, here is the structure of graphite. Now if you are looking at the structure of this graphite, okay, I think I'll magnify this a little bit, then after that I can write in the form of points. Okay, let me magnify this and now see the picture of graphite. Now there are different layers. So if you look at this, this is the first layer, here this one is the first layer, and this is what is the second layer. Now later on a question comes, sorry, this is the second layer and this is the third layer. So that means altogether you can see here 3 layers are there. You know, one layer is connected with another layer by small dot lines that you can see, that blue green dot lines. That is what is called a van der Waals force, and van der Waals forces are one of the weakest force excuse me, weakest force. And because of that only, now a question is asked, why is graphite very slippery? So it is because of the fact that these layers, parallel layers which are there, are connected with each other through van der Waals force, which are very weak and can be easily broken by small stress. A small physical force also can break it. So because of which graphite is usually very slippery to touch, and that is why we say usually graphites are also used as dry lubricant. Okay, now you can see this is how the carbon atoms are connected with one another. You can see this kind of hexagonal ring is what is formed. Yeah, each of this one connected to another one in one layer, again another layer, third layer, fourth layer, it keeps on going on and on, something like this is what happens. Now let us see then about graphite. Now if I tell you about graphite, the first thing that you should know about graphite is, number 1, I think I shall write here, is like unlike in case of your diamond, the carbons, all carbon atoms are sp2 hybridized. Okay, this is the first thing that you have to know. Then it has a layered structure. Okay, now second one, even though I have already pointed out why it is layer, you can see first layer, second layer, third layer. In the diagram you can see 3 layers are there. So it has layered structure, and we call this layer structure as flat and parallel. Flat and parallel. So they are flat and parallel structure. So then each layer has a carbon atom which are arranged in regular flat hexagon. Okay, so hexagon, as you can see, hexagonal ring, as you can see 6 carbon atoms are connected with one another. So each layer, so if you are talking about layer, so each layer has a carbon atom. So these carbon atoms which are arranged in regular flat hexagon. So regular flat hexagon is, and yes, you can see that in the diagram also. Let me point it out here also, that carbon bond length is 1.42 angstrom. So that is what is the bond length. And each layer, okay, this is now important. Now each layer is linked to the other layer by a very weak force. Okay, one layer, let me write it this way, one layer connected with another layer by a very weak force, and that force actually is van der Waals force. So that is why you know that graphites are usually slippery to touch. Yeah, this is will complete in fact your syllabus, that is the first chapter syllabus. So solid state. Now since we are finished with the first chapter, in fact I have taken this mode of teaching. Now maybe in the second chapter I'll use some other mode of teaching. Okay, so till that time, yeah, I may put this notes, in fact structure, especially the structure of these 4 crystals, you need it, so I may put a PDF file there in the download description. You can download it, and if you want you can copy it in your copies. It will be easy for you to study the structure. Okay, thank you.